Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the normal force. So this is one of those videos in what I would like to call a series of follow-up videos to my Newton's law and introduction of forces videos. These ones are to discuss some specific forces and how they work and how to sort of account for them. So one of the specific forces that I want to account for here is the normal force. I've already, in some sense, done one specific force, which is gravity, and we may want to revisit that one in today's video briefly. And of course, I will have a whole separate video to discuss the idea of normal force and gravity working kind of together on inclined planes and how to handle those. Today, I just want to do the normal force as such. So what is the normal force? Basically, the normal force is essentially electrostatic repulsion, but on a macroscopic scale. The best way to maybe introduce it is to consider that you can have something like a table, let's say, or even the ground, but I'm going to draw it as if it's up on a table. And now I put an object with some mass on top of that table. So this has some mass. It's now sitting up here on this table. And that means that gravity is pulling on this object, which is sitting on this tabletop. And so if all I have is just gravity acting downwards, Fg, that would be m times g. If that's all that I have acting on this object, then the object should accelerate downwards. However, we know from experience that unless the table collapses, the object does not, in fact, accelerate downwards. In fact, it can just rest on the table. So in order for that to happen, in order for this object to rest on the table, there must be some second force acting on the object to keep it from falling and accelerating downward. So the net force must be zero. The sum of forces acting on this object must be zero. But we know that this right here is not zero. So this does not equal zero. The logic of this situation suggests that there must be another force. So therefore, another force must be present. Okay. Second thing that we know about this system, about this force that is coming into being, is that it can change. It doesn't have to be a constant force. It can change in response to essentially how hard the object is being pressed onto the table. If I take my hand and if I take a table, this isn't a table, but it's a box, it's a solid box like a table. If I take my hand and I push lightly on it, then I feel a force upward on my hand from the box. And if I push more firmly, then the force that the box applies back up on my hand increases, and essentially increases to counter however hard I push. That is in some sense Newton's third law, of course, but here we have a table, we have an object, we have gravity, and we have some additional force resisting gravity and any other forces that we may apply downward on this box. Okay, second thing that we observe is that this force that's being applied on the box from the table, it only is there to resist the box's falling through the table. In other words, if I took that same table and I replaced it with the tabletop with ice on top of the wood, or if I put an oil slick along the top of the wood of the table, then if I tried to push left or right on the object, it would more easily slide than if it's just sitting on the wood of the table. Okay, so that kind of counters friction in some sense. That allows us to account for friction between the two, which is a topic for another day, of course. But if I push straight down on it, even if there's oil, even if there's ice, even if there's whatever, it continues to resist moving straight downward. Okay? Well, straight downward is perpendicular to the surface. So we could say the resisting force is perpendicular to the surface which is applying it. So again, if I draw this little cartoon of an object on the table, maybe just from the side like this, I have on the one hand gravity that's trying to pull the object downward. And then on the other hand, I have from the table some force that is upward like this. And since this is a perpendicular force to the table, we sometimes call it the normal force. When we say that two vectors are normal to each other, we mean that they are perpendicular to each other. So this force is perpendicular to the surface which is applying it. So this is, we call it normal force. It's represented variously by an n, a lowercase n, and usually when I write it, I use an F with a subscript of an N or a capital N. So I prefer F with a subscript to just simply using the letter. Okay, so in some sense, we have 2 points that we can say about the normal force. One, it's perpendicular to the surface that's applying it. Two, it's variable depending on how hard the object is being pressed into the surface. Note that that second clause, it's determined by the force with which the object is being pressed into the surface. That second clause does not mean that normal force and gravity are always equal. Case in point, I could have a box like this. So again, here's my surface. Could have a block like this. It has some amount of gravity acting downwards. And then it may be that I am trying to lift this object, or maybe me and a friend are trying to lift this object. So maybe it's no longer on a table but is on the ground. So we're lifting up, we're lifting up. So this would be like F1 and F2 from me and from my friend. Well, the normal force then will only be more like this rather than the full length of the gravity. So in this case, we could say something like sum of forces equals 0 implies that the normal force plus F1 plus F2 is equal to mg. And so long as F normal is greater than or equal to 0, the object is not lifted. Now this statement may seem very simple, but it actually can be broadened a bit. Essentially, this force Fn between an object and a surface is the contact force between the object and the surface. And that means that as long as that force is greater than or equal to 0, meaning as long as it is upward away from the surface in some way, it follows that the object remains in contact with the surface. So that's true whether we're trying to lift it. That's true later when we talk about circular motion with roller coasters. If the roller coaster is at the top of a loop, it remains on the track as long as there is a normal force required to sort of keep the centripetal acceleration. It's true of cars going over a hill. So, you might have like a little slope like this, and you got a car that's moving along the slope. So if this car is, or this truck is moving along the slope, it remains on the slope as long as there is a non-zero normal force. So as long as Fn is, we could say, out of the hill or slope or surface, then contact is maintained. And that means that this truck will not like fly off the hill. So if the normal force falls to where the logic of the situation would say the normal force has to be inward or downward rather than upward, then that means that this is no longer making contact, and maybe you've got a situation like this going on where you've gone so quickly up the hill that you don't end up just driving down the other side. Instead, you kind of like jump the hill. Okay. Another situation, if you have something like a wall, so here's a wall, and you have an object that you have placed on the wall. If you press on this object, like so, and you apply like an F push, then this wall is going to apply back a normal force that's equal to that pushing force. Now notice that if there isn't a third force present here, or if I don't push upwards at an angle, that this object should actually slide down the wall. That actually helps imply the existence of a third force, friction, which in this case would be an upward force to balance out gravity. Coming back to all three of these situations that I've drawn, we might ask, and this is the subject of another video that I'm doing, if I take the table that this object was on originally and I tilt it somewhat so that instead of being horizontal like this dashed line, it's off at some angle, what does that do to the normal force? Well, you end up with gravity still being straight down towards the Earth. So mg is still down like this. Your normal force, however, has to remain perpendicular to the surface. So this is now my normal force, and it's perpendicular to the surface that it's on. Notice that that means that gravity and the normal force cannot add to zero. In fact, if I took this gravity force here and I moved it tip to tail here, then I would end up with something that goes only to right here. So this right here would be Fn, and so the difference between this point and this point is your net force between those two. Now typically on an actual surface you might also have another force, friction, present, which maybe is in this direction. So we would have friction right here, and so if you added that to these, it may be that you have a total force of 0. But the point here is that my normal force has to be perpendicular to the surface, and so if I rotate the surface, I will change the direction of the normal force, and I may also change, as it turns out, its magnitude. Okay, that's all that I'm going to do in today's brief video. Hopefully you have some more ideas about normal force. Hopefully you've learned something good from this, and thanks for watching.